Advancements in container ship technology have transformed the shipping industry since its emergence in the 20th century. This concept was pioneered by Malcolm McLean, an American entrepreneur, with the aim of addressing the challenges of slow and costly loading and unloading processes. His innovation focused on developing cargo containers that could be easily transferred from trucks to ships without the need to open and unload their contents. Ultimately, this laid the foundation for modern container transportation. In 1956, McLean and his company Sealand Service introduced the first commercial container ship called the 𝗖𝗿𝗃𝗃. This breakthrough revolutionized the way goods were transported, and since then, the use of container ships has continued to grow and become the standard in the shipping industry. Today, we are witnessing significant developments in the evolution of container ships with the launch of the 𝗤𝗂𝗃𝗃𝗀𝗃𝗀. This container ship is the world's first autonomous electric vessel, developed by the Norwegian fertilizer company Yara. The ship's launch is part of Norway's commitment to achieving a zero-emission vision by 2050. In tests conducted in November 2021, 𝗤𝗃𝗃𝗀𝗃 successfully demonstrated its ability to autonomously load containers and transport up to 100 containers. What's fascinating is that this ship can operate entirely without the need for human crews, relying on technology and computer systems. The vessel's power capacity of 7 megawatt-hours is equivalent to the power generated by 90 Tesla cars. This advancement reflects the progress in technology and innovation since the early days of container ships and provides an indication of a bright future in cargo transportation. Before 𝗤𝗃𝗃𝗀𝗃 was constructed as a physical ship, a model of the ship was tested in a testing facility to ensure its efficient operation. Building a ship like this involves strict supervision at every stage, from design to launch. The ship's design and construction process is complex and time-consuming, with attention to every detail. While modern 𝗖𝗍𝗃𝗃𝗀𝗃 technology has made this process more manageable, dimensions, hull shape, significant ratios, configurations, and the center of gravity must be carefully considered. Usually, ship models are not made of the same materials as the actual ships, such as steel, due to considerations of availability, practicality, and differences in buoyancy needs. Instead, commonly used materials include wood, wax or paraffin, FRP or fiberglass plastic, and lightweight metals. The model-making process involves creating a negative model, or plug, which is then coated with a release agent and shaped with layers of fiber soaked in resin. This mold is used to produce a number of ship models as needed. Milling machines are used to ensure the accuracy of shape and waterline. The creation of ship models involves hydrostatic calculations before the production phase, and small errors can have a significant impact on the ship's design. High-level computer technology has facilitated this process, allowing ship models to be created similarly to actual ship construction. Ship models are usually designed to mimic specific types of ships, such as bulk carriers, tankers, and barges. However, simple models are also used for basic studies like resistance and propulsion calculations. The choice of ship model testing facilities depends on the experimental objectives to be achieved. All model-scale experiments are conducted in freshwater with various shapes and dimensions. The towing tank is the primary experimental facility used to measure and solve ship hydrodynamics problems. It was first introduced by William Froude in 1870. This tank is used to measure resistance on ship models. The towing tank resembles a long pool with shallow depths of around 100 meters. While the tank's width is limited, it allows various experiments related to a ship's motion within a certain distance without significant lateral movement. These tests help measure resistance, propulsive power, displacement, propeller submersion, trim, speed, and engine performance. However, the narrow width of the towing tank restricts experiments involving the ship's lateral movement. For maneuvering tests and other experiments involving sea conditions, wider basins and channels are used. The towing tank is equipped with temperature control systems, humidity control, air circulation, and other environmental conditions because changes in water temperature can affect test results. When testing ship models in the towing tank, the models are usually mounted on a carriage that moves along rails on the tank's side to record vital data, computers, and other data collection systems. Researchers and observers can also observe the experiments from this carriage. It should be noted that the towing tank has limitations due to its narrow size and shallow water effects, which affect the ship model's hydrodynamics. Therefore, ship model testing in the towing tank is usually focused on experiments such as calm water resistance, open water propeller test, and self-propulsion test. The calm water resistance test is used to measure a ship model's resistance under calm water conditions without waves and helps predict the actual ship's resistance at various speeds. The open water propeller test assesses the performance of ship propellers or blades to improve thrust efficiency and reduce fuel consumption. The self-propulsion test involves testing both the ship model and propellers simultaneously, measuring torque and RPM to select and design the propeller according to the ship's needs. In addition to the towing tank, ship model testing can also be conducted in facilities known as wave basins, which have larger widths than towing tanks. Wave basins are used to test a ship's behavior in wave conditions, including wave decay tests and maneuvers such as zigzag, spiral, or circular rotations. Seakeeping is a ship's ability to maintain stability and performance while sailing in open seas or wave conditions. The wave basin's waves can be adjusted according to testing requirements, and this facility is also equipped with wave absorbers to dampen waves after testing is completed. Some wave basin facilities have developed computational fluid dynamics (CFD) software based on data obtained from testing, allowing 3D simulations to replace conventional testing. In addition to the towing tank and wave basin, ship model testing can also be conducted in facilities called wave flumes, which create a testing environment more similar to actual sea conditions experienced by ships. These flumes have relatively larger widths than towing tanks and can be used for more realistic testing. Ship model testing in wave flumes also involves creating waves using mechanical methods, allowing for more realistic testing than in towing tanks. These facilities also create diverse ocean topography to test ships in various seabed conditions. In the development of this technology, ship model testing using 3D simulations has become more efficient and accurate. This reflects the importance of ship model testing in modern ship design and research. In addition to the mentioned ship model testing facilities, there are also other facilities used for testing and developing ships, such as high-speed water tanks. These tanks are specifically designed to test ships at high speeds and are a crucial part of research in optimizing ship performance, especially for high-speed vessels like patrol boats or fast passenger ships. Testing in high-speed tanks allows engineers to understand how a ship will behave at high speeds, including the aerodynamic effects on the ship's hull. Furthermore, recent advancements in sensor technology and monitoring have transformed how ship model testing is conducted. Advanced sensors attached to ship models can collect real-time data during testing, which can then be analyzed to identify a ship's performance in various conditions. This enables engineers to make faster and more precise decisions in developing more efficient and safe ship designs. In addition to physical testing, computer simulations have become increasingly important in modern ship development. By using simulation software, engineers can accurately predict how a ship will behave in various conditions without the need for physical model testing. This helps save time and costs in ship development and allows for more complex and repetitive experiments. Through a combination of physical testing, advanced sensor usage, and computer simulations, ship development has reached unprecedented levels of sophistication, ushering the shipping industry into a new era of innovation and efficiency.